Welcome back. In this video, I'm going to discuss component-based lowering and hauling systems for lightweight technical rope rescue. If you're watching this, I'm going to assume that you've already watched my videos on friction hitches and force limitation, or you have a solid understanding of those principles. This discussion will build on those concepts. Many rescue teams use purpose-built devices like the MPD or clutch to control both lowering and provide progress capture on raises. There are a ton of good reasons to use those devices. However, they are heavy, expensive, and they only work on 11 to 13 millimeter ropes. So many teams are choosing to use component-based systems instead for lightweight rescue. A component-based rescue system is comprised of a descent control device, or DCD, an auto-stop backup, pulleys, a progress capture, usually friction hitches, along with a combination of soft goods and carabiners. When you're putting together a component-based system, there are a few design elements to consider. First, the system needs to be strong. If you're following the concept of force limitation, you should shoot for 18 to 24 kilonewtons as a goal for the weakest links in the system. The system should hold forces of up to 6 kilonewtons and then slip and re-grip with minimal slip distance, somewhere between 6 and 12 kilonewtons, to absorb and reduce maximum arrest forces. The system should function if an operator either loses control of the brake or overrides the auto-stop mechanism. It should stop a rescue load within a meter or so when subjected to a significant impact like an edge transition gone wrong, and it should still be fully functional afterwards. Perhaps most importantly, the system should be easy to operate and use relatively common equipment such that if a device breaks or is dropped, it's possible for the team to continue the operation. As I've mentioned in my other videos, the combination of devices and materials matters. Not all combinations or configurations will work together. So if you're building a component-based system, please test your system to ensure that it'll function in a worst-case load event. I titled this video, Where to Put the Prusik, because realistically there are two ways to configure a component-based lowering system, either with the auto-stop friction hitch on the brake strand behind the DCD, or on the load strand in front of the DCD. Basically, both options work fine. But there are some considerations to keep in mind. So let's talk about putting the friction hitch on the load strand in front of the DCD first. Placing a friction hitch on the load strand is super simple and it works with most descent control devices, including the Munter and Super Munter. It also makes changing over from lower to raise and passing knots on a lower a step or two faster than using a friction hitch on the brake strand. If an operator loses control of a system with the friction hitch on the load strand, that hitch will hopefully take the entire rescue load. If you're using a single 3-wrap nylon Prusik in that configuration, testing shows that it might glaze and fail to hold the load, or fail outright, resulting in the rescue load going to the ground. That is bad. If it does grab, then it will be probably impossible to release without some hijinks. So if you're using a friction hitch on the load strand, it's better practice now to use a Technora sheathed VT Prusik from Blue Water tied in a Valdetan truss or max over 1 configuration. That heat resistant cord reduces the chance of damage because remember, we want the system to remain functional after an incident, and it's more likely to be releasable under load. However, I have seen reputable testing on smaller diameter ropes, including the Sterling 9.5 Canyon Tech, where in a max over 1 configuration, the VT Prusik on the load strand wasn't releasable after the drop. So it's a good practice to attach that hitch to the anchor using a load releasable hitch, just like in the old days of tandem Prusik belays. Now let's look at a system with the friction hitch behind the DCD on the brake strand. In this configuration, you gain some flexibility in materials choice. A VT Prusik in a 3-wrap or max over 1 configuration works well on most rescue ropes, and a variety of 7mm and 8mm 3-wrap Prusiks have been tested to function with most rescue ropes as well. If you're improvising in a mountain or self-rescue situation and using thinner recreational climbing Prusiks like 6mm or 5mm or even a Sterling hollow block, then I would definitely choose to place the Prusik on the brake strand behind the DCD because it's going to see less force. In terms of drawbacks, putting the friction hitch on the brake strand requires extending the anchor with a jumper and then redirecting the brake through the master point. Since the load will always sit on the descent control device, the operator will have to create a tension transfer using another strand of the rope or a set of fours on the load strand to change over from lower to raise or to pass a knot when under tension. Some teams have found that certain nylon 3-wrap Prusiks tend to loosen up when they're not being actively managed on the brake strand. So backing the system up with a knot when the operator is not actively managing the system is more critical than with other configurations. Finally, it's important to note that this does not work with a munter or super munter, as the brake position on the munter or super munter is forward, not back. So to summarize, the pros to using a friction hitch on the load strand are that it makes for easier transitions and requires a slightly less complicated anchor. The cons are that it requires a specialized piece of equipment, that is a Technora sheathed VT Prusik, and some additional technical knowledge in tying a max over 1 and a load releasable hitch. The major benefit in placing a friction hitch on the brake strand behind the DCD is that it allows more flexibility in terms of materials and hitches, but it requires a jumper and a redirect on the anchor, adds a step to loaded transitions or knot passes, and it does not work on a munter. Ultimately, both options are fine so long as you test your materials combinations to ensure they'll function in a significant load event. In both configurations, proper training is necessary to ensure that the operator doesn't override the auto stop, and using techniques like the hitchhiker method or smoking the Prusik will help reduce the chance of that human error. I've also seen systems that use a mechanical backup, like the Petzl shunt or Gibbs rescue sender, in place of a Prusik, and that's acceptable so long as that device has been tested to slip and re-grip at a predictable force. Otherwise, the system might end up transferring extremely high forces to the rescuer and the patient in the event of a worst-case load. As far as hauling with a component-based system is concerned, there's less to say. You just put a Prusik on the load line with a Prusik minding pulley. I would err on the side of beefier 7mm or 8mm pre-sewn Prusik cords because they become the sole life safety attachment for the load when hauling. If you're using a Blue Water VT Prusik, you might consider using the distal hitch variation as it minds better than a Valdetin Tress or Max over 1 on Prusik minding pulleys. There is a ton more information on these hitches in my video on friction hitches. Before I wrap this up, I'd like to mention toothed cam devices as progress capture. Toothed camming devices have become popular with some rescue teams, particularly in the wildland fire rescue world. Devices like the Petzl Micro Traction, the Pro Traction, and the Tiblock are commonly used by recreational big wall climbers to haul loads. They're used in crevasse rescue by guides and recreational climbers, as well as by top rope soloists to attach themselves to fixed lines. However, the max forces associated with those systems are vastly lower than what we can create in team-based high-angle rope rescue scenarios. It doesn't matter if you follow a static safety factor or a force limitation model, using a toothed cam device as progress capture causes these systems to fail the design criteria. Petzl claims that these devices will de-sheath the rope at 4 kilonewtons. There's some real-world testing from How Not To that shows that in reality the failure point is more likely closer to 6 kN, but regardless, that is an exceedingly narrow safety margin for high-angle rope rescue. So if you're choosing a toothed cam device as your progress capture, I would strongly encourage you to alter your system to a purpose-built device like the MPD or clutch, or to use friction hitches and Prusik minding pulleys instead. If you find yourself in a situation where using a toothed cam for hauling a rescue load is unavoidable, then it's important to severely limit your haul factor. Use load cells in real time to keep forces low. Keep good eyes over the edge and continuous communications with the litter attendant, and go to great lengths to avoid getting the litter hung up or the rigging hung up on the raise or on the edge transition. It would be terrifyingly easy to create a critical system failure if any of these things go wrong on a toothed cam device. As a reminder, this entire discussion about component-based systems is irrelevant if you choose to use 11mm ropes and a pair of purpose-built devices. I have it on good authority that there will be a new generation of lightweight purpose-built devices available soon that will work with smaller diameter ropes as well. When this happens, hopefully we can shelve all the scarabs and Prusik minding pulleys and enjoy the convenience and safety of purpose-built systems for lightweight rescue. In the meantime, though, drop test your setup and stay proficient at those tension transfers. That's all I got for you now. As always, citations and additional reading are in the description, and I'll look forward to your comments and questions. Thanks for watching.